Alright, hi everyone, welcome to my YouTube channel, City of Electrons. So in this video, we are going to talk about two-port network for BJT. Two-port network, so device effect of ROL on RC. Okay, now this is a simple two-port network. Note that there is no load. There is no load. So current in, impedance in, voltage is one part of the network, is on that part. So two-port network. AV is the voltage gain at no load. AVNL. AINL equals 0 because there's no load. Okay, so the current gain equals 0. Now NL, I just said that means no load. Okay, and voltage gain is output voltage by input voltage. So that means the output voltage, if you cross multiply, this comes this way, the output voltage will be what? AVNL, and then multiplied by input voltage VI, where VO, output voltage, is the Thevenin voltage, that's ETH, okay, which equals voltage gain at no load. Okay, yeah, it's Thevenin voltage. So let's quickly work an example on that. Okay, quickly work an example on that. So sketch a two-port network of the figure below. Now looking at this, of course this is a bipolar junction transistor we have here. Okay, so now to calculate this, we have to sketch a two-port network. That means to sketch something like this. And in order to sketch something like this, what we need to do first is to know our ROE value. Okay, this ROE value, we have done this in, I think this video, I think, yeah, transistor model. We did that on that transistor model. Oh, but we have done a lot. Please guys, check out the previous videos. We have done a lot and they will really help out. So where are we now? Okay, here. So we'll calculate the ROE value, and by the formula, experimental value, by formula we have it as 26 millivolts over IE, where IE equals IC plus IB. Also done this before, and IE knows that IC is what? The same as beta IB. We've done this also. Oh, a lot. IE. So of course IE will now give us this value. Okay, so to calculate IE, we need to know IB, and to know IB, we need to do this analysis from the collector to emitter part. VCC, the voltage drop at this point, which is this. This is what we are doing now. Okay, base emitter part. So this is VCC, and this is ROB. The voltage drop here is what? IB ROB. Then the voltage drop here is what? VBE. There's no voltage drop because 0. So that's what we have here. So you just make IB subject formula and you get this. Now you plug in your value. VCC is 12, VBE is 0.7, ROB is what? This. That will give you IB. Now you substitute this into what? Equation 2, which is this guy. So you put IB here, and then you get IE. Now you can substitute IE into equation 1, which is ROE, and that will give you your ROE. Good. Now we can say the output impedance is called ROB in parallel with beta ROE. How? Right here. How? Right here. This same diagram, guys. This same diagram. Okay. I think I have that thing here. Where? Yeah, look at it. Okay. Yeah, beta ROE. Now, but in this case, come back here. But in this case, our beta ROE is parallel to what? ROB, because we have ROB in this case. Yeah, we have ROB in this case. Okay, so it's parallel to ROB, where beta ROE is what? And beta is 100, ROE is what? This. how is beta 100 is given in the equation, given in the diagram. Beta is 100. Okay, so this guy here, we are just simplifying it here, parallel network. So ROB, this ROB, beta ROE, this beta ROE, ROB is ROB plus beta ROE is ROE. That gives us our input impedance. So at no load, output voltage gain at no load equals output impedance over ROE. ROE is this. Output impedance is the same. Look at it. It's the same as what? This guy here. If you look at this example here, output impedance. Output impedance is the same as ROC. I think I solved that somewhere. Can't you look at it? Blend ZO. Okay, the same as ROC. So progress. Okay, this way I am now. This way. Where are you? Okay. So we just put in that value here, this over this, over RE, and we get our voltage gain at no load. Okay, voltage gain at no load is what? Output voltage over input voltage, which is also equal to this, and we've calculated it to be this value. So now when you draw this same diagram with this one here, same diagram, but the difference is just that in this case we now have values to them. Okay, so the same diagram, you just put in the values ETH there. Okay, ROC is the same as Z out and Z in. Okay, then for cascade representation, to represent it in form of cascade, same thing. Okay, look at this one pointing up, this one points in. For cascade, this one points up, this one points in. Same thing. Okay, then this one points up, this one points in. This one points up, this one points in. Just like for cascade, you have something like a triangle pointing to your right, while here you have a rectangle. That's just the simple major difference. Here you have your ETH, here you have your ETH, and inside there you have ground. And that resistance, look at it here. Look at it here. Same thing, guys. Same thing. Okay. So that's it for no load. So for when there is load, I'll just do it together, because when there is load, okay, no, let's just do a different video on that. So the one I did just now is for no load. So we'll work on the one that has load in the next video.